Okay, so we're going to jump right in and try to get as much of this figured out before class is over. I don't know where our stopping point will be, but I would love if we could make it all the way to the end of the back. This unit is kind of like a 3-lesson unit. So if we don't quite make it all the way to the end, then we won't, and that's okay. All right? So here we go. Y'all ready to get started? Man, all that excitement in the air. All right, so here we go. First of all, we're starting out talking about monomial. Y'all know what the root word is there? What's mono mean? Did you not get it? Yeah, mono means one, right? So when we talk about a monomial, we're talking about a single term. A single term. Now that single term could look a variety of different ways. It could just be a number, right? It could be just like 8. Vaughn, it could also be just a variable, like x squared. But it also could be a combination of the two, 8x squared. And I'm telling you, there's a lot of ways we could write these. Alex, I need with me. Okay, here's the key. To make something not a monomial, it's done. To make something not a monomial, it would have had to have had a certain mathematical operation between terms to make them separated. What are those mathematical operations? Addition and subtraction. You're exactly right. If there's no addition or subtraction to separate terms, it's one term. I mean, seriously, look at this. This would be a monomial. 7x to the 5th, y, open parenthesis, 4x to the 3rd, y squared, raised to the 5th power. I mean, that's one term, believe it or not. It obviously needs to be simplified. But what do you not have in between terms? You don't have any plus signs, you don't have any minus signs. So technically that is one term. Okay? That's one term. That's a monomial. It's got some numbers, it's got some variables. Now, we're going to know how to reduce a problem like that using some of the rules that you've either learned in the past and you remember them, or maybe you learned them in the past and you didn't remember them, and then maybe a couple that you haven't learned in the past. Here's the one that I promise you guys have learned. It's called the product rule. It's saying if I have the same base, and they both have exponents, and I'm multiplying, all right, I can get those together. The base will stay the same, but we do what with our exponents? We add them. We do m plus n. Y'all done that before. Think about it. If I have x squared times x to the 7th, what does that turn into? Well, the base stays the same, right? X. But how many exponents do you have now?
It's like x to the 9.
It's x to the 9th. Yeah. So you've done that. You've added exponents because you're multiplying and your bases are the same. You've done that. So that's a rule that you're familiar with. You're also probably familiar with the power rule. The power rule is a little different because it only has one base that has an exponent, but it's being raised to another exponent. Now, won't my base stay the same? But this time, I'm not going to do what with my exponents? I'm not going to add them. This time, when I have a power to a power, I do what? I multiply my exponents. I multiply. Here's why. It's like I'm saying, hey, I have x squared 7 times. If I have x squared 7 times, it means I have x squared, x squared, x squared, x squared, x squared, x squared, x squared. So how many would that all be? X to the 14th. Y'all understand? Y'all done that before, haven't you? property or rule that I think you've definitely done before, and that's division, the quotient rule. If I had, for example, a to the m over a to the n, so my variables or my bases are the same on both the top and bottom, numerator and denominator, I can combine those, but how do I do it? Would you say, Lewis? Oh, you didn't say it? You subtract them. You do m minus n. You subtract them. So an example of this, using the same values, x to the 7th divided by x to the 2nd. Right? Same base. So we can combine these. What do I do with my exponents? 7 minus 2 equals 5. Now there's a caveat to that. And we're going to talk about that in a minute. But it all has to do with where is the variable bigger. Here, wasn't the variable bigger in the numerator? And that's where the answer ended up. What if that numerator or that variable would have been bigger in the denominator? Well, wouldn't have x on top. You'd have something else. Yeah, you'd have 1 on top. And your x would end up in the denominator. Okay? So, those three I'm confident you've talked about before. Those three. Now, here's one that I don't know if maybe you've ever talked about. And we're going to add it. And it's a to the negative m. Now, a lot of us would look at this and think, it's fine, it looks fine the way it is. I don't disagree with you, but math doesn't like negative exponents. So math likes you to get rid of negative exponents. And to get rid of a negative exponent means we need to make it positive, right? Now listen, all numbers could be written as a fraction, couldn't they? Fraction has a numerator and a denominator. Is a to the negative m written as a fraction? No. Could I? What could I do to make it a fraction? I could put it over 1, couldn't I? Would I change the value of it if I put it over 1? No. So technically, a to the negative m is in which location? It's in the top. It's in the numerator. So here's the deal. In math, they don't like negative exponents. So to get rid of a negative exponent, we change the location. You see, you just told me that it's in the what? Numerator. We're going to move it to the denominator. When I move it to the denominator, it'll turn that negative exponent to a positive exponent. Now listen, you got to have something in the top, don't you? You can't write a number that has nothing in the numerator. So what do we always put there? A 1. So that's how you deal with negative exponents. You change the location. I like saying it that way, change the location. Instead of saying move it to the denominator, I like saying change the location because here's the deal. What if the negative exponent is in the denominator? Do you put it in the denominator of the denominator? No. You change its location. If it's in the denominator with a negative exponent, what do I do with it? Move it to the numerator. And that will change that negative exponent to what? To positive. So you change the location. That's what I like to say. So for example, let's add x to the negative 2. Again, technically, where is that right now? If there's no fraction, I know it's in the what? Nuh-uh, it's in the numerator. So I put it where? I put it in the denominator, and that turns that negative 2 into a positive 2. Now, you got to have something on top, right? So we put a 1 there. We put a 1 there. And then the last rule that you may not be as familiar with is the 0 exponent rule. If I had anything raised to the 0 power, what is the solution? What is the value? It's 1. It's 1. Here's how I like to describe this, and I think it makes more sense now after what we just did. Someone tell me, what does x squared mean? It means, real simple, tell me the real simple explanation of what does x squared mean? means x times x, right? Guys, what does just x to the first or x mean? It just means x. Now, go back to what we just learned. I'm going to skip down to x to the negative 1. What does that mean? It means the x has to change what? Locations. So it goes to the denominator, and it's just x down there. Right? What does x to the negative 2 mean then? It means that x squared goes to the bottom. So here's the way I like to explain the zero property rule. Look, what did I skip right here? I skipped x to the 0. So here's how I like to describe it. X to the 0 is that location where it's transitioning from the numerator to the denominator. It's that transition for where it is on top of itself. And what's anything divided by itself? That's why anything to the 0 power is 1, with one exception. 0 to the 0 power. Wouldn't that be where 0 is on top of itself? Well, all of a sudden I'm going 0 divided by 0, and am I allowed to divide by 0? No. So what's the answer to 0 to the 0 power? Undefined. Not 0. It's undefined because I'm not allowed to divide by 0. You can't divide something by something that has no value. It's impossible. It's undefined. Okay? So, therefore, x to the 0 will give me the value of 1. Now, I want to show you guys something because then all of a sudden, it brings in this difference. And I want you guys to see the difference right now. You ready? Is there a difference between negative x to the 0 and negative x to the 0? Is there a difference between these two problems right here? What do y'all think? I told you that something to the 0 power is when it's on top of itself. So is there any difference between these two values? Yes. Okay, here's why. In this first one, what's being raised to the 0 power? Just x. Negative's out in front of it. So negative stays out in front of it, and just x is over itself. Making the result what? Negative 1. But in this one, what's being raised to the 0 power? See, because of the parentheses, this is the location where negative x is on top of negative x. And what does that turn into? Positive 1. So please know, there is a difference when that negative out front is in parentheses versus not in parentheses. You with me? Okay, so let's get back to these problems, okay? Let's get back to the problems. An example here would be, let's say in parentheses, we got 7x squared, and I'm raising it to the 0 power. What's the result? Not 0, it's 1. Right? That's the moment where 7x squared is what? Over itself. 7x squared over 7x squared, 1. So that's the 0 rule. Y'all got it? That's the 0 rule. 1. You know when we've seen this in the past, we've just allowed it to cancel. Like for example, isn't x over x technically x to the 0? But what do we always do with x over x? We let it cancel because it equals what? 1. It just cancels because the value is just 1. So you've seen this before, but you probably just never thought about it from that perspective. Now, let's move along to some pretty challenging problems using these rules. Y'all ready? Everybody ready? Because these can be pretty challenging sometimes. Here's what I ask. When we're doing these different rules, you've got to remember, treat numbers like numbers. Treat exponents like exponents. You see this 2 right here? Is that a number? Yeah. But we don't treat it like a number. We treat it like an exponent. Same with this 6 right here. Let me explain why. What I'm saying. Right here, we're doing what with these 2 monomials? We're multiplying. We're going to treat numbers like numbers. If I'm multiplying, what do I do with numbers? I multiply them. What is 5 times negative 7? Now, 2 and 6, do I multiply them? No, they're not numbers. They're exponents. Remember the rule? When I'm multiplying and my bases are the same, the base stays the same, and we do what? We add our exponents. 2 plus 6 is 8. So, treat numbers like numbers and exponents like exponents. Distinguish them. They're not the same. That's why we have these exponent rules, because they're not the same as numbers. You don't treat them the same as numbers. You with me? So that one's pretty easy, wasn't it? Let's move to this one. They kind of get more difficult as they go, kind of. Let's look at this one. First, y'all know that before you multiply, you have to raise this to the power of 2, right? Exponents come before multiplication. PEMDAS, right? PEMDAS. PEMDAS. I mean, it's the same. Y'all know it, right? Exponents come before multiplication. So we need to square negative 2a cubed b. Remember, treat numbers like numbers. What's the number in that parenthesis? What are we doing with negative 2? We're squaring it, right? That's what that means. So what does it mean to square negative 2? We multiply it by itself. What's negative 2 times negative 2? 4. So we treated the number like a number, but the exponents, am I going 3 squared? No. It's a power to a power. This is power rule. And what do we do in exponent rules when we have a power to a power? 3 times 2 is 6. It's like we have a cubed twice. Y'all understand that? It's like we have a cubed twice. And that becomes a to the 6. What do we technically have here? B to the what? We have b to the first, technically, right? So that is 1 times 2, b to the second. So that becomes 4a to the 6, b squared. Y'all with me? Now can we multiply this by 8ab to the 9th? All right, so treat numbers like numbers. Guys, what's 4 times 8? 32 is my number. Treat exponents like exponents. I have the same base of a, don't I? So we can multiply those by doing what with the exponents? Add them. We've got 6 and 1. What does 6 and 1 combine to get? 7. We got both have base of b, so we can combine those by doing what? Adding. So 2 plus 9. So this becomes 32, a to the 7th, b to the 11th. You with me? Y'all doing good? Not good? Caleb, you good? Yeah. Okay. Because I saw a face. Was the face a not good face? Or was it a good face? Good face. Okay. I like good faces. Let's go to 3. Guys, what comes first? Quotients or subtraction? Yeah, division, right? Division. This is before subtraction. So let's divide. Will 54 divided by 3 turn out as a nice number? Try it. 54 divided by 3. One more up. It's 18. It's 18. Now look at this, guys. Here's how I like to do these. Where is m bigger? So it stays up top, and we subtract from the top. What's 6 minus 2? M to the 4th. Where is n bigger? So we keep n up top. We subtract from the top. What's 4 minus 1? 3. Now, guys, are we allowed to subtract 10 m to the fourth n cubed? Okay, I'm going to ask y'all a real quick question. What's 18x minus 10x? 8x. What is 18 m to the fourth n cubed minus 10 m to the fourth n cubed?
8.
It's 8. Why do we do that? Why do we overcomplicate it? Let me ask you a question one more time. What's 18x minus 10x? 8 what? Did your variable change? So why all of a sudden if I say, what's 18 m to the fourth n cubed minus 10 m to the fourth n cubed, do you want to change your variable? Do we change our variable? No. Here's the best way I can describe this. Are you going to listen to this? I think it's a brilliant thing. If I had 18 guys minus 10 guys, would I end up with 8 chickens? No. When you're subtracting like terms, your terms don't, what? They don't change. Don't think that, oh man, now we're not dealing with x, now we're dealing with m to the fourth n cubed, it's got to be different, and they're going to check. No. When we add and subtract like terms, your variable stays the same. Okay? So, it's 8 m to the fourth n to the third. That's a common mistake that we make. Too much. Don't make it. Adding and subtracting like terms means your term stays the same. Okay? You just add or subtract the number. Term stays the same. Y'all with me on that? Okay. So let's make sure we don't make that mistake moving forward. Okay, this one. We're multiplying. Now I know I see a negative exponent too. But let's multiply first and see what happens. Treat numbers like numbers. What's 2 times 10? 20. And treat variables and exponents like exponents. We have k, both of these, right? So we can combine these by doing what with our exponents? Adding, right? When we multiply and our bases are the same, add exponents. What's 4 plus negative 7? Negative 3. Now, does math like this answer? Nope, math doesn't like it. Because what has a what? What has a negative exponent? Okay. Does 20 have a negative exponent? No. 20 does not have a negative exponent. Here's the point. Does 20 need to move? Does 20 need to change locations? No. But the k that's in the numerator does, right? Where does it need to go? It needs to go to the bottom. And what will happen to that negative 3?
Positive.
Turns positive. Y'all with me on that? Okay, number next. Well, next one. Sorry. Number 5. Treat numbers like numbers, right? So let's take care of the 2/3 squared. Doesn't that mean we go 2/3 times 2/3? What's 2/3 times 2/3? Let's just multiply at the top. 2 times 2, 4. 3 times 3, 9. So 4 over 9. Now, r squared, squared. Remember, treat exponents like exponents. When we have a power to a power, what do? We multiply. 2 times 2 is 4. How about s? 14. Y'all getting it? Times 1 over 6 r cubed s, which has nothing we can do yet. So let's finish this thing out. Let's treat numbers like numbers. What is 4 over 9 times 1 over 6? Go to your calculator for me real quick. Remember, your calculator is awesome at doing fractions. So go alpha y equals number 1 and do 4 over 9 times alpha y equals number 1, 1 over 6.
2 over 27.
So I'm going to put 2 up top over 27 in the bottom. Now, we're going to multiply our variables now. You got 2 options. When I do r to the 4th times r to the 3rd, it becomes r to the what? 7th. And when I times s to the understood first, what does that become? S to the 15th. So listen, here are my two options. I could have left it like this, the way that the problem was written, where you have the fraction out front, and then you have the r to the 7th, s to the 15th, kind of like right in front of it. Technically, when it's right in front of it, though, where is r to the 7th, s to the 15th? Is it in the numerator or the denominator? Y'all know? It's in the numerator. So some people don't like to be confused, so they put the r to the 7th, s to the 15th up top with the 2, and then they put the 27 in the bottom, because the 27 is the only one that's in the denominator. And that's fine too. Both of these answers are 100% fine. Just know, when you see your variables out in front like that, it means technically they're in the numerator. Okay? They're in the numerator. All right. Number 6. Number 6 is way easier than sometimes people think it is. Remember the rule with negative exponents? What I said? You got to change the location. Well, look. What's being raised to a negative exponent? A fraction. What can I do to a fraction to change the location? Well, the numerator needs to move where? To the denominator, and the denominator needs to move to where? The numerator. So it needs to flip. And when I flip it, doesn't it change that negative exponent to positive? So if it changes it to positive 1, does positive 1 even really help me? So here's my problem I'm working with now. So let's focus on 7 over 14. Does it just divide away? No, it simplifies. What will 7 over 14 simplify to? 1 over 2. 1 over 2. 1 over 2. Now, here's where I go like this. Where is W bigger? It's bigger in the bottom. So where am I going to go put W? Nah, it's bigger in the bottom. We're going to put it in the bottom. And we're going to subtract from the bottom. What is 12 minus 3? So our answer, simplified, is 1 over 2W to the 9th. Vaughn, you with me on that?
Yeah.
Really? You don't seem it. You seem a little distracted. Are you?
No.
Yeah, you are. All right, I'm going to do one more. And what time will we get out here? It's 11:16. 15. So I'm going to get done a little earlier than I had planned for a couple of reasons. Because I think we're in a situation where if we kind of kept moving forward, we would get stuck in kind of no man's land. And I'd rather get to a definitive stopping point. So stay with me here. I'm actually going to do 2 more, okay? 2 more. So look at number 7. 15 over 24. That doesn't just divide out to a nice number, does it? But we can reduce it. What's the best method of reducing it if you don't know how to reduce? Alpha, y equals number 1, and just type it in. It will simplify it for you, just like that other one did. What do you get? You get 5 over 8. Are y'all all with me? Now, how do I deal with these x's and y's? Where is x bigger? Then where will x be? And where do we subtract from? So what's 12 minus 10? So it's 8x squared right now in the bottom. And then where's y bigger? So where will y go? And where will we subtract from? 4 minus 3. So I leave it 5y over 8x squared. Don't overcomplicate it. Okay? Back when I was your age, we used to always subtract from the top. So I would have done 10 minus 12, and then guess what I've gotten? Negative 2. And then it's like, oh wait, math doesn't like negative exponents. Change the location. We'll put it in the bottom, make it positive. Why? Just go where it's bigger. Subtract from there. Okay? Don't overcomplicate things. So that leads me to this last problem we're going to do, number 9, on the back. We're going to stop right here. After we do this problem, you can have a billion answers for this problem. The question says, Give me an example of two monomials with a quotient of. What's quotient mean? We're dividing. And what does the result of our dividing need to give me?
-3 and square root of 2.
Okay, so let's start with the -3. Somebody tell me two numbers that we can divide where it would leave -3 in the numerator. 9 and 3?
Yeah.
But one of them needs to be what?
Negative.
So does it matter which one?
No.
So let's just make it what?
9 and
-9 over 3?
3.
Is that good? It's funny. The last two classes chose the same two numbers. I mean, you could have done something. You could have done 6 and 2. You could have done 12 and 4. But the last three classes have done 9 and 3. Weirdos. Y'all are all weirdos. Okay. I'm joking. So now let's go. What's the next variable? M or N? No, M comes before N. Where did M end up? So let's do M on both top and bottom. But we're going to write this in a way where it's bigger, where? On the bottom, by how many? 1. It's going to be 1 bigger in the bottom. So let's write this in a way where it's 1 bigger in the bottom. M squared on the bottom? Well, there you go. It's bigger in the bottom by 1. We could have done so many things, couldn't we? Could we have done m to the 8th over m to the 9th? I mean, you could have done so many things. Now, last thing, we have n. Let's write n in both places. What's the rule here? What has to happen here? It's got to stay in the top. By how many does it have to be bigger? It's got to be 2 bigger in the top. It's no fun. I want it better. That's no fun.
Fine. End to the 9th.
Okay, end of the 9th,
And then end of the 7th.
end of the 7th. Man, let's do fun numbers. Y'all are boring.
We're not the boring.
Boring
You're
numbers.
the boring
Boring.
one.
You're boring. Boring.
You're the boring one.
No, you wanted to do easy. I wanted to do exciting. Okay,
No. You're the
so
boring one.
here is your homework. And I'll tell you which numbers here in about 2 seconds. Let me get them all passed out.
I didn't realize.
Who's boring? Who's boring? Me? I'm the cool one. Everybody else is the boring one.
You realize you're still recording.
Now I'm still recording. I don't even care. What are they going to do to me? Fire me? Huh? Come on.
Ow! Why'd you hit me?
Lies.
Oh my!
Lies.
Oh,
Lies.
right in the face!
Okay, your homework, ready? Is number 2 through 12. No, I'm sorry. Pause. 1 through 8.
2, 3, 12, and
1 through 8.
How do you even go from
1 through 8. We haven't done 9 through 12.
a little slow today.
We haven't done 9 through 12. That's tomorrow. So tomorrow we will jump in and cover some more of this. But tonight, I want you to do 1 through 8. Okay? No homeroom today. Well, unless you're not going to the thingy thing. The what is it called? Yeah, the Renaissance little Renaissance thing.
Wait, hold on. Is that right now?